Welcome to our lab video of a severe soft tissue Aquinas contracture. We'll be using a Hexapod frame to correct this over time with distraction. Clinically, in the operating room, it would be important to release any soft tissue contractures concurrently. You don't want the frame to be doing everything. You want to have restored as much soft tissue stability and balance through your surgeries and balancing posteriorly, lengthening the gastrocs, etc., as you can to minimize your risk of recurrence. For frame positioning, I like to start with the foot ring, and we want to make sure that our first wire is placed perpendicular to the axis of the foot and parallel to the floor. So here I've got the foot flat on the table, and we're driving a level wire. In the operating room, you can use the lid of an instrument tray or just match it up with your eye. So here we are relative to the bottom of the foot. That's something we'll be able to accommodate with our fixation points. As you can see, we drove lateral to medial in the posterior aspect of the tuber, somewhat low. Lateral to medial is against the typical teaching for going from danger to from safety to danger. However, here, because our posterior medial to anterior lateral wire has to start medially in order to maintain accurate placement, we do the posterior tuber wire lateral to medial and have to be extra careful clinically to avoid the neurovascular bundle. So then we want to set up our fixation points so that the ring is in the plane of the foot with enough clearance posteriorly for the calcaneal tuber and soft tissues. We can provisionally tighten that in an acceptable position before we move on to the posterior medial to anterior lateral olive wire. This gives us an opposing olive wire setup, which maximizes our stability. The other component of that stability is maximizing the divergence. So a divergence angle will be maximized by having a posterior medial to anterior lateral start point. I'm just making the whole thing level in order to facilitate later steps. And here I'm going to shoot along the ring so that it should come out in a place that we can fix directly to the ring. 2 more wire fixation bolts, and we'll have our provisional fixation of our distal component. And there's our provisional fixation of the foot. In surgery, all of these would be tensioned to 90 pounds posteriorly and about 90 pounds here, and we step down about 50 along the transverse as the ring will buckle. We're going to look for a pathway here where we can get a transverse fixation through the metatarsals. It looks like we'll be able to do it right off the ring. And I'm going to see if I can catch 5 in order to maximize our stability. So we've got an above to below configuration. We can accommodate that with 2 posts. I'm placing them distally because I want to avoid the connection points of the struts if I can. And you want to be sure to maximize your proximity to the frame if possible. You'll have more stability with a 1-hole post with a wire than a 3 or a 4. And we'll tighten everything just to keep it from slipping. For this wire, it doesn't matter which side you tension on. For the olive wires, you have to tension on the away from the olive wire ball. So we're going to do a little bit of a tension maneuver here. Can't quantify it directly, but it does allow some component of tension to do a Russian tightening, where we'll put both wrenches together and rotate that fixation point. So you can see we've tensioned that wire and it no longer deflects significantly with pressure. In contrast, the olive wires that we didn't tension deflect fairly significantly. Clinically, all of those would be tensioned in the operating room at this stage, pulling the olive wire down and tensioning away. But for the sake of time, we'll move on with our proximal ring fixation. I've set up this proximal ring with the typical configuration of struts and the 5/8 ring posteriorly. So we have short struts in the back and long struts in positions 3 and 6, as well as 1 and 2. Now we're going to tilt the bone to match us here to place the anterior or proximal fixation. I'm going to tilt the proximal ring to be perpendicular to the bone segment. So we've set our ring perpendicular to that axis and given ourselves adequate soft tissue spacing. In the operating room, we pre-drill every hole. Here we're going to pre-drill just this first one to save time. But this is one that we want to be careful to watch that it goes perpendicular to the bone segment. And these would usually be placed by hand, but to be faster, we'll use the power. So we can now start to lock in our proximal ring fixation. The ability to swivel the ring through the pin fixation bolt allows me to fine tune it before provisionally locking it in finger tight, as well as to rotate to create soft tissue space if needed. And then with 2 10 wrenches, we'll be locking in the post as well as the pin fixation bolt. Double check our mounting to make sure we're happy, and then we can move along with our additional fixation points. 3 half pins is plenty. You want to maximize both spread distance and spread angle. So we've got a 5-hole above for a tower, a 1-hole below, and another 4-hole below. In the operating room, this would be placed by drill technique, we would drill while irrigating and then place the half pin. But for the sake of time, we'll stick with power. And then we'll tighten up. We have one more fixation point to add. Then we'll hook up our struts and record that. I'm going to move this fixation point a little more anterior. And we'll add a direct medial half pin. Have our final fixation above and below at this point. The next step is to hook up the struts. In this system, there's pre-defined points in the ring for each strut. If you get yourself into trouble and have to veer away, there are rescue tabs. And then there's a hex nut buried into the ring, along with a torque wrench to optimize the connections. It is important that you don't use a non-torque wrench because the screw can be stripped. And it's also very important that the laser line on the strut, which you can see here, be sunk all the way into the ring so that it has stability. I'm adjusting the gradual distraction so that I can get it in place. Get it placed in up to the laser line. And then do our tightening with the torque wrench. We now have our fixation finalized. At this point, we would bend off all of the wires and cut the pins. But we'll do that off camera to be more efficient with your time. You can see the mounting to the foot. Pretty happy with our perpendicularity there, as well as the mounting proximally from a perpendicular standpoint in the AP and in the lateral view. Welcome to the post-operative planning of the Hexapod Aquinas frame with this system. I've gone to here and add new patient, which brings us to this screen. We're entering just basic patient data. In this example, we'll focus on the planning software only. And we can go to Save and Create Case. This brings us to the initial case data. It's a deformity frame. Our frame ID is A, as it's the first frame on this patient. The case ID can be the case description, again, whatever you choose. This sawbone is a left, and we'll use the ankle mode. For our deformity parameters, we've shot our reference x-rays down the proximal ring, so we're going to use a proximal reference segment. And we have the option of doing the traditional manual measurements or the digitally based planning software. We'll be using the digitally based planning software in this example. Our first step is to acknowledge that we will not place PHI on the website, which is pretty easy since there isn't any for this one. And we'll be doing post-operative planning only. For Aquinas frames, I don't think that preoperative building is particularly effective, as there's usually some correction through soft tissue releases in the operating room. We initiate by loading our pre-op AP image. It's going to bring it up. This is appropriate. Medial is labeled medial and lateral is lateral. We confirm our rotation. Now we can do our calibration. We placed a mag marker, mag ball in this example. So we put the edge of our circle on one extreme of this mag ball and the other on the outside. You can zoom in and increase your precision. You may find in some cases, especially if the image is shot oblique to the receiver film, that your mag ball gets elongated. It's important to know that you can never make it smaller by angulating your film or your beam, since it's a sphere. So now we're going to go to our lateral and do the same thing. We're going to bring in our lateral film, a proximally referenced lateral film ideally, since we've chosen proximal referencing. Now we'll calibrate again. Again, we'll use circle, zoom in enough that we're confident in our accuracy. So here we have a slight diameter mismatch. I make it match the lesser diameter, as we previously discussed. There was likely some plate obliquity on our lateral film. Now we place our osteotomy. For an Equinus frame, it's perpendicular to the mechanical axis of the tibia at the level of rotation of the talus. I'm going to move this based on my estimation of center. Move this distal just a little bit to match. And I'm confident in that. So we'll lock it and move to the next step, which is our deformity analysis. In the coronal plane, we don't intend any deformity correction. We'll remind ourselves of the deformity principles in the coronal plane. The lateral distal tibial angle should be 90. And we'll take out any translation. That could be done fairly quick and dirty, as long as you keep the deformity parameters what you expect. For this Aquinas frame, the lateral analysis is more important, obviously, because that's the plane we plan to correct in. You can extend the drawing lines and then swing them so that they're parallel to the bottom of the foot. And I like to carry them up so that they touch the bottom of the metatarsal head and the bottom of the calcaneus. You can see there's image manipulation tools on the side to make that more visible. And now we're going to have it come up through the sustentaculum, and theoretically our apex should be right at the osteotomy, right at the center of rotation of the talus. You can see it brings in a fairly aggressive suggested bone lengthening when we do this because of the large deformity that we've modeled.
You don't have to follow that, as we'll see. So we like our deformity analysis. I'm confident in my lines. It fits with my preoperative analysis of the x-rays, and I'll move to the next step to fine-tune my correction. It's automatically put in that 17, but I'm going to turn it down and say that 5 is enough in this case. Somewhere between 5 and 10 millimeters is typically enough to distract the joint to avoid impingement. It is very important to watch these patients during correction to make sure the anterior talus does not contact the anterior plafond. My habit is to overcorrect into 5 degrees of calcaneus to give a little extra stretch to the posterior soft tissues, and you can see how easy it is to dial that in around our rotation point with this software, and we're going to lock it in. The post-op x-rays I'm going to show you will be back to neutral after this overcorrection, just to illustrate the point of a fully corrected Equinus with good accuracy with this system. Now we can do our mounting parameters. We have 160 5/8 posterior ring proximally and 160 foot plate distally. That bring that up, we can see that the level of the ring is the same in both images. That confirms that I placed the osteotomy level at the same anatomic space on the AP and the lateral. We can see that the rings on the AP and the lateral are very closely represented by their CAD drawings. This shows that we did our magnification marker well. This frame is not externally rotated in this example, at least relative to these films. So we're going to lock and go to next. And as we move, it's going to take us back to the standard planning software. Make sure you save. And all of our work from the digital planning software is now here. Our mounting parameters are automatically brought in, as well as the deformity parameters. We're now going to enter our strut sizes and lengths. We have 4 longs and 2 shorts, with the shorts on 4 and 5. We've recorded our strut measurements from the operating room. To be more efficient, you can use tab to get between. And I'm going to take a few seconds to double check them. My typical practice is to have someone read me the numbers and me enter them separately in order to minimize errors. This is one of the places where we can still make a simple mistake that could create a fairly bizarre result. So I've just double checked them. And saved and updated, which brings us to our initial position. This does look like the frame that we have on. You can see there's an alarm for impingement distally on 4 and 5. We'll get into that further on the next screen. And this is the predicted end result, which is what we would like, 5 degrees overcorrected. Sometimes I'll dial this back to neutral right before removal, fairly acutely. We're going to move to our next page while we discuss this further. There's no latency for soft tissue frames unless there are pain problems for the patient. I stick with 4 adjustments a day for tolerance, but I tell them they can pile them up if they need to, because we're not worried about bone healing. And we're going to set it to 2 degrees per day. This again can be modulated based on patient's tolerance. It's going to bring up the impingement again once we run this. It reminds me again, remember you have impingement on strut 4 and 5. We're going to move on to the next step to discuss what that means. And you'll see, most likely, that at the beginning of the plan, it's unhappy with our position posteriorly. So there's an alarm through the first day that this strut is impinging, both struts 4 and 5. There'll be some warnings that I need to navigate through. I have to check carefully to make sure there are not other impingement areas. What it's warning me is that either the rings or the struts are at or near their limit of angulation or length, and that I need to double check. Since I know I was able to get this frame on and that it was stable and everything was locked in, I trust that this warning is at but not exceeding the limit, and I'm comfortable to proceed. Note that the frame does not know, in this version of the software, where your fixation points are. So this does not tell you strut impingement versus fixation elements. It's just the rings and the struts themselves. Now that I've checked it all to be sure that my impingement is what I suspected, I'm going to generate the patient's prescription. Here's what the patient is given, along with their daily strut changes, whether they're going forward or backward. When you go to give this to the patient, it's very helpful to use the provided direction markers to tell them on 1 and 2 they'll be turning negative. 3, 4, 5, and 6 will be turning positive. It's worth double checking that. Here we see strut 6 makes a shift on day 65, so that would be a time to bring the patient back and change the direction marker. And we are confident with this plan as it is. We're going to hand it to the patient and move forward. We keep this, that has all of our strut adjustments and strut changes. The long light color indicates your window for exchange, and the darker color is your deadline for exchange. When you come back to make that change, you can click here on that day and propose, if you're not using the last deadline day, you can propose that strut, and it will tell you the most efficient way to use this strut on that day would be to set it to 19 and 80, and that will carry through the rest of the software. So you don't have to bring them in 3 times for all these strut changes. You can bring them in when all the red and blue are overlapping. It's very difficult to eliminate strut changes in severe Aquinas frames. We're going to accept that change to strut 4. Carries that forward to the end. Thank you. Here we are at our final corrected position after reducing back to neutral but keeping the distraction. We can see neutralization of our Aquinas. Throughout the process, there was no evidence of impingement of the anterior talus on the anterior plafond, and this frame is now ready to remove.